All right. So then, without further ado, it's really a pleasure to be able to introduce Dr. Hari Viswanathan from the Los Alamos National Laboratory. Hari is a member of the SMART team and actually leading our Task 7 work in the oil and gas realm, and he's been at Los Alamos for, well, I don't have how many years he's been at Los Alamos, but it's been I guess close to 2 decades that I've known him. It's been a pleasure working with him over the years, and he's going to talk to us today about physics-informed machine learning for real-time unconventional reservoir management, some work that's being done that is directly related to what we're doing here in SMART. So without further ado, Hari, take it away.
Okay. So yeah, thanks for the opportunity. So what I thought I would do is, this is a presentation that George Guthrie and I put together that we gave to headquarters a couple of months ago, and it sort of describes what we've been doing on our fundamental shale portfolio and how that's been feeding the new SMART initiative for Task 7. And so the general topic here is increasing reservoir efficiency from unconventional reservoirs using a science-based approach for reservoir management. And so what we've been doing on this project, I guess I'll say who our collaborators are on the different pieces. And so on the fundamental shale portfolio, we've got multiple national labs that you can see there: Sandia, Berkeley, SLAC at Stanford, NETL. And then on the SMART initiative with MCL, we're working with WVU, that's done a lot of the initial work on the MCL site, Northeast Energy, and NETL contributes to all parts of this. And so why are we focusing on reservoir management? We thought this is something that could be a pretty quick win in that how you manage pressure in a reservoir, if one of the goals for SMART is to take physics-based models, but to sort of accelerate them to be able to make real-time decisions. Pressure management is something that you could manipulate pretty quickly and see how that affects production. And, science-based, I think everybody on this call knows why that would be. If you want, just empirical methods that are very much, fitting the problem, you're going to do poorly if you now change, if your training set is no longer valid, if you're operating under a different set of conditions. And another part of, one of the challenges of these unconventional systems, as we're all aware, is, they're fractured reservoirs where the structure of your fractures and the connectivity matters quite a bit on how that controls production. And so if you're sort of looking at just traditional machine learning approaches, one of the big successes and why machine learning has been so successful recently is that very large data sets have become available. So whether you're looking at image identification, self-driving cars, these are very large data sets where you can then interpolate and do an extremely good job. And those are many of the breakthroughs that we've seen. Some of the challenges for what we're trying to do in subsurface have some challenges when it comes to machine learning, basically because we often do not have that kind of density of data. We're somewhat data limited. And, but therefore, that's one of the reasons kind of science-informed machine learning makes a lot of sense, because if we're trying to get away from just interpolating within a data set, but now you need to be able to extrapolate to a new set of conditions, you want to basically take advantage of what machine learning can do, but also put in the kind of physics constraints that'll prevent you from, allow you to adapt to a new set of conditions. And so some of the things that we want to be able to do is, can we make early decisions on a site before more of the site data comes in? And as the site data comes in, can we bring that in and make our corrections even better, our modeling better? And, we're focusing on pressure management. And so as I'll show you in what we've been looking at, there are different drawdown scenarios that can increase the efficiency of production. So one of the main hypotheses of what we're trying to do is if the subsurface is somewhat data sparse, can we then augment the kind of real observations that we have with synthetic data to be able to enable this extrapolation? And so, there's caveats with that. Obviously, the synthetic data that you put in has to be accurate, and you need to be able to generate it rapidly in order for this to work. And so if you look at this pyramid that we've got, everything on the base of the pyramid that's in blue has been what we've been doing on the fundamental shale portfolio that DOE's been funding for the last 5 years, which has been a multi-lab effort. The Los Alamos part of that, if you look at the two edges of that base of the pyramid, we're basically saying that, well, unconventionals have a few things that make them, physically and chemically different from conventional reservoirs. If you look at the matrix, your pore size distribution in shales can often be an average of less than 50 nanometers in size. When you're down in these very small pores, you now have nano-confinement effects, which actually result in traditional reservoir models from doing a poor job in predicting what is the transport in the matrix. And so we've been trying to characterize the matrix for these unconventionals. On the right-hand side of the base of the pyramid, fractures. So unconventional reservoirs are very much dependent on fracture flow, and how the matrix and fracture interact are very important. In projects I used to work on before unconventionals, you could often get away with homogenizing the fractures because the structure of the fractures didn't matter so much. But for hydraulic fracturing, the connectivity between the fractures you generate and the natural fractures have a huge impact. And so you could imagine a similar fracture density orientation of two different reservoirs that have similar statistics, but one of them is extremely well connected and the other one is not. And so you need to be able to account for that connectivity. If you want to do that with your standard physics-based model, that could be computationally expensive because of the kind of meshing you'd have to do to deal with all these fractures, which you also don't know where they all are. So you have to deal with that stochastically. So I'll show you some examples of what we've been doing on both matrix and fractures. And then how do we feed this into a reservoir model that can now account for this kind of new mechanisms and being able to do it fast, because we want to be able to generate a large amount of synthetic data that would be used to enable and accelerate these models for reservoir management, with one of the keys of SMART being able to do real-time decision-making, history matching, as well as virtual learning. And so I guess just a few notes on, this whole concept of being able to accelerate physics-based models and taking advantage of what machine learning has to offer kind of permeates the entire Los Alamos portfolio, because, there is weapons research at Los Alamos. Clearly we're not doing any nuclear testing for a long time, but Los Alamos needs to be able to extrapolate to say if the stockpile still works. For nuclear nonproliferation, we're interested in actually physics that is quite relevant to hydraulic fracturing. If you have underground nuclear test from another country and you're trying to figure out are gases going to seep to the surface, it's actually fractures that are interacting between the generated blast and the background fracture network that leads to seepage to the surface. Again, that's an issue where you're not going to know exactly where every single fracture is. It's going to be statistical, but you need to deal with the connectivity. And so there's a lot of programs that we've been working on in addition to this one that require being able to have physics-based models to enable machine learning to be more capable of extrapolating and being able to do it quickly. And so this project fits in very nicely with that general idea. And so now kind of tunneling down into what we've been doing with pressure management. Uh, so if you look on the top right, these are two different pressure drawdown scenarios that we're just showing conceptually. And this has been written about by many different people in the literature. We're actually working with Mukul Sharma on this project as well, who's done work on this. And so the idea would be, if you draw down on an unconventional well rapidly, you might actually get more gas or hydrocarbon out quickly, but then you could plateau because during that rapid drawdown, the relationship between pressure and stress and fracture aperture, you could actually end up closing off a bunch of fractures. And so the rapid drawdown case that's shown in blue, you actually, you get out more quickly, but then it levels off. There's been a lot of anecdotal evidence from the different companies that we deal with that say, well, if you're more slow about drawing down the well, you may not close off more of these fractures due to that, however, you don't get as much out early, but you might get more out eventually. So it may be more sustainable. We definitely need to bring in economics in connection with this, because, the early money that you get from producing could be worth more than later money. So it's not as simple as just looking at when the two drawdowns cross over, but you also have to include the economics as well. But this is actually, this is just kind of the type of examples that if you are efficient in how you do your drawdown strategy, and you're able to almost have something that has the advantage of the physics-based model, but you're able to do it on the fly, you would be able to really manage your system much better. So that would be the general gist of what we're trying to do. And then the picture, so we're developing this kind of predictive basis for trying to forecast gas recovery under these different pressure management scenarios. And so the top right picture kind of takes the previous case and sort of says, well, we know that the slow drawdown and rapid drawdown scenarios actually have quite a bit of uncertainty. And as you run multiple realizations, you're actually going to get different behavior. So you're never going to know the exact truth, but you need to be able to get these two envelopes nailed down. And so and then the bottom right, kind of, many of you on the call might even be part of this portfolio, or at least you're aware of it, but DOE fundamental shale portfolio has very much been looking at, if you had an idealized production curve, there's going to be different mechanisms that control early production. For example, early production can only be produced from fractures that are large enough to conduct enough flow and hydrocarbon to produce, enough to the well quickly. And then as you get into sort of the middle mechanisms, that could be smaller fractures, that are also, when you integrate under the curve, they still make up quite a bit of production. And then as you get to late-term mechanisms, the matrix very much comes into play. How does the shale matrix interface with these smaller fractures that eventually feed the larger fractures? And so if you look at the different national lab projects, they're basically doing experiments and simulations that are pretty well integrated to basically figure out how can you optimize different parts of this production curve. And it's just kind of a closer look at that. And all I want to say is that it's been, a really good program to be a part of, because, for example, if we want to look at geochemical effects on how, precipitation and dissolution reactions in the matrix can affect production, SLAC has been doing those type of measurements. We also do neutron experiments, and so SLAC gave us samples, which we run in beam time, and we're able to look at which part of the shale matrix is accessible before the chemistry and after the chemistry. And so just want to emphasize that the sum of this portfolio is much greater than the parts, and I'll give you a few more examples, and we are bridging quite a few scales here. And I don't want this sort of violates what you would usually show in just a single slide, but I just want to sort of show how this work is organized. So our LANL portfolio, we've had internal LDRD work on this to be able to accelerate physics-based fracture models, because, as I said, fracture models matter across the LANL portfolio. And so that's LDRD is internal funding for us. The shale portfolio is what we're showing in red. And then SMART is our new initiative for, which we're doing in MSEAL. And then we also have follow work in this and technology commercialization projects to take some of the software we're developing and commercialize it. But you might say, how do all these things link together? I think the goals on the right-hand side are actually something that I'm going to walk you through in the rest of these slides. So I think it's important to take a look at that. The matrix, which is the top row, what do we really care about? We care about the mass transfer of hydrocarbon as it leads to the matrix. And so we asked our experimentalists and modelers down at that scale to do some pretty fancy Lattice-Boltzmann model, neutron scattering experiments and so on. What would be the abstracting equation that you would feed us? And so that would be kind of a rate of hydrocarbon that goes against a constant. That constant is the ratio of accessible pores in the shale matrix to the total pores times the diffusion coefficient times the pressure gradient. If you look at the fractures, we're very much interested in the aperture B, how that changes due to stress. And so if you're drawing down, different drawdown scenarios are going to close up your aperture to a different extent. So we've been measuring in the Marcellus and at MCL what are the different parameters that would allow us to capture that process. If you look at the fast, accurate simulation row, the general gist of that is we have discrete fracture network models that can run on HPC platforms. These can be pretty computationally expensive, and we still don't know where every single fracture is going to be in the subsurface. It's got to be statistical. So our internal work has very much said, how do we use graph theory? People might not know what graph theory is. It's basically just studying and being able to study connected systems. And so fractures are connected systems. So is all this epidemic spreading, even the COVID spreading right now, people are looking at using graphs for doing that at Los Alamos. It's just how are connected systems characterized. And so we can take a discrete fracture network model, which would be a finite element model, convert it into a connectivity graph and do much quicker reduced order models, kind of in the form that reduced order models have been used on NRAP that I think many people on this call are used to as well. And so we're accelerating models with a combination of graph theory and machine learning. And then in the bottom one, we're now demonstrating this pressure management on MCL on SMART Task 7. And so now I'll just kind of go through fairly quickly some of the highlights of what we've been doing. So I'll go into some of the highlights and what we've been doing with the shale matrix, and I'll go through this fairly quickly. So remember, what are we doing for the shale matrix? Just keep your eye on, we need to be able to inform what's the mass transfer of hydrocarbon coming out of the matrix. Why? What's the big deal about the matrix? Shale matrix has this pore size distribution that averages 50 nanometers in size, and when you're down in pores that are less than 50 nanometers in size, things start getting very different from what a typical flow is going to be. Let me explain why. So when you're down in, let's say, a 10 nanometer size pore, the number of molecules of, for example, methane that can fit into that pore is very few. So in typical fluid mechanics, you might think about how does flow move through a pipe or a slit pore? You would have a parabolic velocity profile, and you're going to have a stick boundary condition at the two edges, right? You're going to have friction that basically causes the flow to be slower at the edge than in the middle, which is what gives you the parabola. But what happens when you're down in these kind of nano-confined pores, and there's a lot of work in Office of Science in this area, is that the number of interactions between just fluid, which would be methane in this example, actually, the collisions between just fluid actually ends up being not nearly as much as just fluid with the wall. And that results in things like a slip condition at the boundary. what this actually does is you could end up getting 100 times greater effective permeability in these nano-confined pores. And it actually changes your viscosity, your density, your absorption. Everything changes quite a bit. And even then, it's still a nano-Darcy permeability thing. But when you connect this kind of matrix to small cracks, those are effects that you have to be able to consider. And one of the reasons unconventionals produce as well as they do is due to some of these advantages that occur through nano confinement. So what we're showing here is Lattice-Boltzmann modeling. It's also backed up by experiments that show that you can get greater than about 2 orders of magnitude in effective permeability due to these nano confinement effects. And that can directly be fed into the equation that we're showing up there. And then experimentally, we developed a neutron method to be able to probe the transported nanopores. And so what this is doing is it's trying to figure out it's quite difficult to do these experiments because the pores are just so tiny. But we're able to explore what percentage of the pores are open and accessible versus which are closed. And this is all fairly new things that are having to be figured out because unconventionals have become such an important thing. If I go to the next slide, this is some of the things that we're pretty excited about. We've just submitting a paper to Nature Communications on this, which is with these neutron experiments, if you look at the left, if you have an unpressurized nanopore, you don't have that many molecules of methane that can even fit in there, and that's the pore throat. So then we apply different pressure drawdown scenarios. In general, if you apply a greater pressure gradient, you would expect, more to come out than for the 3000 case, which is a less of a pressure gradient. Both of these are somewhat reasonable. We sort of picked these pressures because they're similar to some of the work Farah Bazadi has recently done. And what's interesting about the results here is that when you apply too steep a pressure gradient, you actually can end up doing irreversible damage to these nanopores, where a lot of them actually end up getting closed off. And you end up getting, and there's also effects like methane swelling the kerogen in these pores and so on. And so it's not completely straightforward, even in the nanopores. I mean, we knew this about the fractures, but even in the nanopores, aggressive drawdown scenarios may close off some of the pores, is what we're finding with this work. And the most recent results is about just a month ago, before everything got shut down. Our experimentalists got the samples from SLAC. We also have some samples from Sandia, and we basically took it to the beam time experiments. And what we're able to see is, barite precipitation is something that SLAC has very much been looking at because it has an NETL as well, Ali and others. Can precipitation have a huge effect on the porosity of the matrix? And so we were able to look at what is the porosity before the chemical reactions and what is it after, and how is it in different lithologies. And so in both of these cases, the porosity decreases quite a bit due to chemical reactions. And so then this is something that we can actively deal with, because depending on what kind of frac fluids we're using, you can either inhibit this kind of precipitation or you might promote it. And so again, pressure management and geochemistry are focuses of fundamental, because those are things operators can actually do to improve the situation. So now we're going to accelerate off into the fractures. And so fractures, we're very much interested in pressure management. How does it close the fractures if you're too aggressive? And that's what that equation is showing. I'm going to pick up my pace a little bit here. But what we're doing is we developed a core scale method for measuring transport property at various stresses. I think this is an exciting branch of research, because I think until hydraulic fracturing really became, this huge thing in the last 10 years, a lot of the rock mechanics work and a lot of the fluid mechanics work were not necessarily coupled, but this is very much a coupled problem where the fluid is now creating the cracks. And so now we have the kind of experimental capabilities to deal with this coupled problem. And I'm going to actually accelerate through this a little bit and just say that we've developed and validated a scalable pressure-dependent model for the MCL core, where we're using a Barton-Bandis model, which is telling you how do apertures close up as a function of stress, and that stress is a function of pressure. And that's something, that's a key mechanism that WVU has told us that's occurring at MCL. I mean, they believe that the pressure management strategy does affect what fractures open and close, and so that very much matters. And I'm going to go to this one. We identified that at MCL that the core might actually be near critical stress. And what that means is, you know, your pressure management strategy is really critical on what kind of fractures can be accessed or not. And so I think the point we're making is a lot of the fundamental work we've done, it actually could make quite a bit of difference. I mean, depending on how you pick your fracturing fluid, you may clog things up or not. Depending on how you do your pressure drawdown strategy, you may close up too many fractures or not. And on top of that, we know there's a lot of pressure to produce quickly because the economics dictate that. But bringing in this kind of mechanistic models, combining it with economics is somewhere where we think we need to go. And so now kind of moving to how do we accelerate these simulations? So we've done a lot of work in just doing discrete fracture network models because in addition to hydraulic fracturing and carbon sequestration, we need this for nuclear nonproliferation, we need this for radioactive waste disposal, and many other things. And so DFN Works is a software platform we developed at Los Alamos that won this R&D 100 back in 2017. And we've used it to do mechanistic studies where we could, you know, see how we're able to match up this production curve and how fracture connectivity affects this production curve. And I think just kind of focus on this table on the bottom of this is just to point out that, you know, fracture production very much dominates production in the early time. But then once you kind of get out to like the 10-year time frame, you could easily have the matrix contributing more than the fractures. And since the wells are already in place, and since DOE very much wants to see sustainable production, we think that there are ways to enhance both the fracture and matrix production through pressure management and effective chemistry management. And so the work on taking these high fidelity models and trying to see how can we simplify this? I mean, if we just take all these DFNs that are running on high performance computing, but we reduce all that connectivity to graphs, and we basically just run much simpler models on graphs, it doesn't give us the same answer as the high fidelity model. But machine learning is very good at looking at complex things, you know, whether it's complex observations or complex simulations, and finding patterns. And so we use machine learning to calibrate these graph models to give us very similar answers to our DFN models, and you can get enormous speed up in doing this. And it's pretty satisfying exercise because it really lets you peel away what level of complexity do you really want in your physics-based model, which things are important, which things are not important. And then also keep in mind, there's so much uncertainty in the system that you can't just get carried away meshing every little fracture, you know, when you're never going to know where all of those are anyway. And so these projects have been very multidisciplinary in nature, where you have statisticians that want to have very little physics in their model, and you have physics-based modelers that very much care about every mechanism, and having both sets of eyes on it, we feel has put us in a good place. And another part of this is pretty exciting is that we never want to be just reinventing the wheel. And so we're pretty happy with how we're able to do fractured systems and graphs and meshing and transport, but how we get those parameters into our models has not been our focus. FracMan has been an industry leader in this for a very long time, and so we have a DOE commercialization project that actually takes the characterization and field observation parts of FracMan and coupling it to DFN Works, and so we're putting those two things together. And so now I kind of give you all the base of the pyramid that we've been doing for quite a while, And this kind of sets us up for how this all feeds into SMART. And so what are we interested in doing in SMART? And so the two parts that we're filling for oil and gas is we're under virtual learning and real-time forecasting. And so what we're trying to do, I'm not going to walk you through every single part of this diagram. It's a bit more complex, but everything above the dashed line are the tools, and everything on the bottom is the data. And we should say that the first part to the left of the vertical dashed line is the site behavior. And so what we want to be able to do is have different site behavior libraries, because we don't want to be tied to any particular physics-based model. We know, depending on, just what the research group is, whether it's industry, which company, which national lab, they all use different physics-based models, which have advantages and disadvantages. And the site behavior library is intended to have kind of a mix of high fidelity runs and low fidelity runs that you can then interrogate. So the focus of the left part of this diagram is to have accurate physics, because again, it's very important if you're going to use synthetic data to inform anything where you're going out into the future. The synthetic data had better be good, otherwise it's going to kind of be a garbage in, garbage out situation. We do want these things to be fast, but fast is not the priority. Accuracy is the priority. Then when you go over to the right-hand side, we are now very much trying to accelerate, and we don't have to be as accurate, in the sense that we've now figured out what are the critical mechanisms and things like that, what are the quantities of interest, such as total cumulative production, total production, stage-specific production, like MCL has this kind of information, other sites may not. And, another interesting part of our MCL project is they've collected so much amazing data, and we know other sites are not always going to have that level of data. So that allows us to peel away which parts of the data they've collected that really helps us and which parts are not going to be as helpful, because we know we can't always collect the level of data that MCL collects. And the other thing I want people to get out of this is, and I think everyone on this call knows, machine learning is a very broad area. So, I mean, when you say machine learning, it's almost like saying mathematics or statistics. You can use it in so many different ways. And so where we think it's useful for our project is to do error correction, to do optimization of this kind of site behavior library that has a bunch of different scenarios in there. We're able to do inversion with it. And so there are many different ways that we're using machine learning on this project. And finally, we also want to be able to use it for forecasting. And so kind of going to this, on MCL, we know that this mechanism is of interest, that if you have aggressive drawdown strategies versus slow drawdown strategies, that the reservoir is going to behave differently. What we've been doing is actually attacking this on parallel lines. One is to develop the kind of ensemble library approach that allows us to accelerate physics-based models. At the same time, we've been working with WVU and NETL to come up with a really nice detailed model that's constrained by data of the site. And the other thing that's been good about this project is we have experimentalists and the field observation people, we have the physics-based modelers and the machine learning people. So having all of those eyes on it, because we're going to have people that are skeptical of machine learning, we're going to have others that are, don't know about the physics of these unconventional reservoirs. We're bringing all of that together. And so on the top left, that would be just one of the stages with a bunch of discrete fractures that are meshing in against the hydraulic fracture at MCL. And then the bottom picture in the center is putting in all of the stages. And MCL has some interesting characteristics. I mean, a lot of the natural fractures are actually plugged up with calcite. So in order to figure out which natural fractures are actually activated, they usually need to be connected to the hydraulic fractures. And so since graph theory is very good at telling us connectivity, it's been a nice way to be able to do exercises of how many degrees of connectivity does a hydraulic fracture go into the natural fracture network. And since we have all this history matching kind of information, can we do the history match brute force, which will be slow? Can we accelerate it and then do virtual learning with it? And so that's sort of just a quick taste. Emphasize that we're just getting going on the MCL smart parts of this. But what we're trying to do is we want to basically figure out what is the level of complexity that's warranted to simulate this site for pressure management. And we're also hoping there may really be chances to try this out, because MCL kind of have an interesting set of conditions where they sell the gas from these wells directly to the town. And as long as that need is met, how they produce the two different wells is actually somewhat something they can mess with, which may not often be the case. And they're not always running these wells full throttle, which is the case in other sites. And so we actually have scenarios where they run this full throttle, other cases where they run it half throttle. So it's really good validation for this approach. And so that's kind of where we're heading on the smart part. And it does feed the fundamentals, because like I said, the Martin bandus and how aperture is definitely affected by the stress and pressures. Those are things that we've been measuring in the lab, and WVU has parameters. We can put that into our physics-based models, and we can also, the matrix work we've been doing also uses NETL and MCL core. And so, Dustin Crandall, I think, is on the call. He's been really good about getting us different samples for these different studies. And again, the collaborations with Slack and Sandia have been very helpful for us as well. And so I kind of just want to summarize by saying that I think that unconventionals are really interesting, and that the matrix and fractures do behave differently. And I think there really is a case where we know that unconventional production efficiency can be improved. And we think that being able to have physics-based models that are fast enough to do this is key, because you kind of need to be able to do this stuff on the fly. And so I think we're putting the different pieces in place, and it's definitely been an exciting project to be a part of. And I just kind of want to leave it at the fundamental portfolio that's been going for 5 years really has been great, because I think people have been doing things, characterizing these mechanisms for unconventional, for early mechanisms, middle mechanisms, and late mechanisms. And, these different research groups have pretty unique data sets and unique models, and being able to put all of that together is what has put us in a position to be able to, feed this into the SMART initiative. And so that's basically what I have. And so hopefully people could understand me. It's hard without having feedback of knowing if people are getting what I'm saying. So I'll open it up for questions.
Thanks very much, Hari. Really great presentation. Do the folks have questions for Hari on the line?
I have a question. This is Sherilyn. Can you hear me?
Yes.
I've been using TrackMan for years, and I was interested to hear about connectivity analysis and graph theory. And I wanted to understand better what the advance is for using graph theory, because I know the software will do the connectivity analysis, but you have to specify how far the fractures are. Are you doing something that, how far out the fractures are, like the degree of connectivity? Are you doing something that teaches the algorithm how to determine that?
So what we're doing is, whether it's a TrackMan type model or any DFN model, you usually are having, a bunch of elements on every single fracture, and then you're refining your mesh where every single fracture connects with the other. And so if we turn that into a graph, there's different ways to do that. You could very simply just assign every fracture to be a node and every connection to be an edge, and then you could have a very simple pipe flow model. If you then just do the physics on that pipe flow model, it's going to be very computationally efficient, but you're going to miss out on all the refinement and advantages of that model. And so what we're doing is actually combining, that very simple thing that captures the structure, but then using a true high fidelity model for the TrackMan or DFN to then learn to be able to get the graph to do very similar behavior to the high fidelity model. And so we've also used graphs the way you're talking about, which is to explore the connectivity of the fracture network to figure out where the flowing backbone is. Because in a lot of cases, what flows in these fracture networks is a very small percentage of the overall fracture. And so, for example, in our radioactive waste work, they actually were able to measure that kind of stuff, right? So only like 1/6 of the fractures flow. And so we use graph theories in different ways, and SMART, what we're using it for, is to really have a really fast fracture simulator that then can be adjusted with machine learning to do something similar to the DSN, so that you could literally have a simulation running, and you could just turn a few dials, and you would see how production is affected just kind of on the fly, rather than having to wait hours for every single calculation, if that makes sense. That's our goal.
So Harry, yeah, great presentation, enjoyed quite a lot. I have a curious question, especially you talk about the gas reservoir for the gas rich compared to the liquid rich. I kind of thinking some like what actually other mechanisms, for example, desorption, that related some like surface of the natural fracture. So is that you have any insights on that or any comments?
So we haven't really looked at that, because everything we've been focusing so far is just on gas and not on oil yet. But yes, I can't really comment on that as of yet. But we do have plans to expand into, but we haven't done that yet. And I guess I should just emphasize, our overall goal is to just make sure that this kind of scenario library approach with physical constraints built in will be good for subsurface problems, that we would be able to get out of cases where we know interpolation is going to work and machine learning is already good for that, and there's really no need for new things there. But a lot of the problems that we work on require a lot of extrapolation, and that's what physics-based models are usually for. But physics-based models tend to be slow. And so I think our niche for the whole initiative would be to bridge that gap.
Yeah, because you mentioned what's actually impact from this kind of study for production. So that's kind of a little bit thinking on that, what's the insight. So maybe, yeah, we can discuss offline as well.
Yeah, okay, thanks.
Thank you.
Any other questions for Hari?
Yeah, Hari. Yeah, this is Hongke from Sandia. Thanks for a nice presentation. I wonder. Obviously, you cover a lot of different kind of aspects and components, and in particular, some you are touching actual multi-scale real problem. And with your kind of framework, conceptually, how do you want to actually deal with this multi-scale kind of features in general?
Yeah, that's a good question. And so that is kind of what we've been doing. Is we have very detailed laboratory experiments or simulations at a given scale, and we feel pretty good about how those are matching up with one another. But as is often the case, as you say, I mean, how do we get the nanoscale effects of the matrix into a reservoir model? Or how do we get the tributary fracture zone, which would be kind of like the tiny fractures that feed the bigger fractures? And so what we've been doing is kind of working with the people at each scale and coming up with as kind of a simple intuitive equation as we can come up with. And so, for example, we just really want to know what is the mass transfer coming out of the matrix. And we know it's kind of this ratio of accessible pores to total pores. And we know matrix diffusion is a key component, and we know the pressure gradient's a key component. So we sort of start with a simple equation like that, and then we try to refine it. Barton-Bandis is another thing that's similar. How does stress and pressure affect the aperture? That's something that people have been looking at for quite a while. So we've been measuring Barton-Bandis parameters for these different rocks. And I think one thing that is important is that we actually feel fairly decent about the physics that are going on at different scales. The bigger challenge is what are the parameters at a given site that can then be used to predict that physics. And so to answer your question, though, we're basically trying to just get different mass transfer rates out of these different scales, and how does that eventually feed what goes into the well. And so we do quite a bit of abstraction at that point, but we have quite a bit of rigorous analysis at each individual scale, and we use our subject matter experts to do the abstraction. Does that make sense?
Yep. Thanks. Yeah, I think, we can probably discuss more details later. Yeah. I have a similar project, so I think, I want to pursue more kind of rigorous approaches.
Yeah, cool. Yeah, right. So I would say what we're doing right now is something that is trying to be computationally efficient and simple. And yes, there are more rigorous approaches which we could discuss.
Yep. Thanks.
Yeah. Any other questions?
Anyone else? Well, if not, then thanks very much, Hari, for a really good talk. I appreciate what you did pulling that together and describing a lot of the work that is being done in SMART and related to SMART. I think it's valuable for everyone to see.
And I will say that now that Task 6 is starting up, I mean, we're having a lot of good discussions because that's a visualization task, and so for oil and gas, and so there's a lot of links to what we're doing here and being able to visualize it in real time.
Very good. All right. Well, then I'm sure we'll be talking again soon, but thanks everyone for joining in on the webinar this afternoon, and we'll have another one. See you back here next week, and everyone take care and stay safe and healthy during these interesting times.
Thank you.